Hello and good morning. This is your instructor Mehak Rohra and welcome to the second session of the chapter Reflection of Light at Curved Surfaces. Before we begin studying what we would be doing in this chapter, let us first have a recollection of what we did in our previous session. Let me remind you, this is the second session of the chapter Refraction of Light at Curved Surfaces. Let's begin by recalling our previous session. So, in our previous session, we went through what basically our basic laws of refraction were, what refraction is, how refraction takes place at plane surfaces, and whether or not these laws of refraction that we studied are followed for curved surfaces. We know that refraction of laws, just like reflection of light, follow for both plane surfaces and curved surfaces. So, change in the path of light ray as it passes from one medium to another is called refraction of light. In physics, refraction does not only take place with light waves but also takes place with sound waves and other waves that you will study in your later classes. So in physics, we define refraction to be the change in direction of a wave which is passing from one medium to another, or a gradual change in the medium. Refraction of light is the most commonly observed phenomenon around us, along with reflection. So, when light travels from a rarer to a denser medium, it will bend towards the normal. When light travels from a denser to a rarer medium, light bends away from the normal. You know, this is due to the speed decrease of light. The causes of refraction is the reason because speed of light is different in different media. Speed of light in vacuum, as you know, is 3 into 10 to power 8 meters per second, but this is not true for light traveling in water, for light traveling in oil, for light traveling in grease, for light traveling in glass. So speed of light differs for different media, and the speed of light is lesser in denser medium while more in rarer medium. So, when speed of light is reduced, it tends to bend away towards the normal. When the speed of light increases, it tries to bend away from the normal. Small I represents angle of incidence here, R represents not angle of reflection but angle of refraction, and E represents angle of emergence. Why do we have another property of E, angle of emergence here? Because usually when we take surfaces, we have the light incident at a particular point, it goes under refraction, the refracted ray travels, and then it emerges from the second point. Since that emergence takes place, we need to define an angle between the normal and the emergent ray, and that counts as the angle of emergence. Refraction of light occurs according to the two following laws, be it plane surfaces or be it curved surfaces. So, the first, the incident ray, the refracted ray, and the normal at the interface of the two media, so at the boundary of the surface where refraction is going to take place. There, the incident ray, our refracted ray, and our normal, they are all going to lie on the same plane. Also, the second, the ratio of the sine of angle of incidence, that the angle that the incident ray makes with the normal, to the sine of angle of refraction, that is the angle that the refracted ray makes with the normal, of any given light, of any given color. This ratio is a constant, and this ratio is equal to the refractive index of the first medium divided by the refractive index of the second medium. That is the ratio, and it's a constant. This is Snell's law of refraction. Refractive index, basically the N1, N2 that you see of different media, this tells you how fast the speed is traveling in a particular medium. If you say that the refractive index of air is supposedly 1, then the refractive index of water is around 1.33. So this is telling you that how fast the speed of light is in water as compared to in air. So this is what refractive indexes represent. So in this particular session, we are going to see some light rays and how they behave when they are going under refraction with two different mediums. Then we are going to derive the curved surface formula for such an interaction of light rays with different media. So if you have object distance, you have image distance, you have the radius of curvature, how are you going to relate them to the refractive indexes of particular surfaces? Then from these curved surfaces, we are going to study the most important curved surfaces when it comes to studying refraction, that are lenses, dually bound curved surfaces. Then we will study some definitions that are related to our lenses, and then we will study the behavior of certain light rays which are incident on lenses and how they will help us draw image diagrams for both convex lenses and concave lenses. Then we would make a summary of what we did in our entire chapter, in our entire session. So let's begin. Special rays considered for ray diagram formation. Right now you have a curved surface which is separating two mediums. Let's say this is air, let's say this is another medium. Or actually, let's say this is one medium and this is the second medium. No need to take it air, because not every time the two medium that are separating a light ray, it's not always going to be air. Sometimes it's going to be glass, sometimes it's going to be water, sometimes it's going to be oil and water. They are going to be definitely different mediums. So it's not right to always take air as the first medium. So let's just say this is one medium, the white part, and the gray part is another medium. So light ray here is going to travel at a different speed, while light ray here in the gray area is going to travel at a different speed. So here we are going to discuss the ray that is traveling along the normal. As I told you, any line which joins the center of curvature of that curved surface to the boundary of that curved surface, that line is going to be the normal. And at curved surfaces you can have many normals. You just don't have one normal like you have in the plane surfaces. So according to Snell's law, you know that this angle of incidence when the light ray is traveling along the normal is 0, because it is traveling along the normal. Incident ray is basically coincident with the normal, so there is absolutely angle of incidence is equal to 0. So when angle of incidence is 0, the ray is going to penetrate and go in the same direction. It's not going to change its direction at all. This is the first case that you have to remember. When light ray travels along the center of curvature or along the normal, it's going to go in the same direction, undeviated. It's going to go and keep going and keep going and keep traveling in the same direction. There is absolutely no deviation taking place. So according to Snell's law of refraction, the ray of light which travels along the normal, it drawn to the surface, does not deviate from its path. So this is the first case. There is a similar case that I'm going to now discuss. This is the one that you see, that is for all normals that are going through center of curvature. There is one special line also that we have to discuss, and that is your principal axis. Again, your principal axis also is a normal. Why? Because this is a straight line. It is touching the surface of your the curved surface that is separating your two media, and it is touching the center of curvature. So this is also a line that is drawn from the center of curvature to the surface of your to the curved surface. So this will also act as a normal. So Snell's law of refraction will be same as it is for this particular ray. This is also a ray which is also represented as a normal. So any ray that is this traveling along your principal axis, so the ray that is passing through the pole and the center of curvature both, they will also go undeviated. There is absolutely no change in this ray, because here if you see, this is also the normal and this is also the incident ray. Since this is the normal and this is the incident ray, the angle of incidence is 0. And since the angle of incidence here is also 0, you have absolutely no deviation. Means there is no bending. The ray came straight and it's going to go in the same direction. Same for this ray. Same for any ray that is going to pass through this particular point C. Any ray from here, any ray from here, any ray. If this point C is what is crossed, they go undeviated. Hence both rays that are mentioned above, both ray traveling along principal axis, ray that is traveling along the normals, they all will go undeviated. So they have to pass through C, the ray that is passing through C, or the ray that is passing through the pole. this is the principal axis, also the normal, this is also the normal, this, and any ray that will pass through center of curvature, they will all act as normals, and hence it will go undeviated. This is important. This is the first two special rays that we are considering for our ray diagram formation. Next, ray parallel to principal axis. Now this is the outward bulging surface here, so it's a convex surface. If you remember the outward curve, if the ray is incident on the outward curve, the curved surface is convex, and if the ray is incident on this inward curve, then the particular surface is concave. So now the light ray here is parallel to your principal axis. This is your principal axis, this is the center of curvature. So this is a light ray that is coming from a certain direction, and it is parallel to your principal axis. You have two types of curved surfaces, as I told you, convex and concave. Right now these two particular diagrams are showing you convex surface interactions. So let us first see convex surface interactions from rarer to denser medium and from denser to rarer medium. Both of these surfaces, if you see, they are convex. Both of the times your incident ray is incident on a convex surface. Convex surface, convex surface. Let's see what happens. A ray which is traveling to a principal axis, it will strike the convex surface, and you see, if you draw the normal, then you will be able to draw a line which is bending towards the normal, right? And it is going to go and strike your principal axis at a certain point, or it's going to meet your principal axis at a certain point, and then it's going to go keep traveling in the same direction. Let's look at figure B. Now the ray is traveling from a denser medium to a rarer medium. Since the ray is traveling from a denser medium to a rarer medium, light has to bend away from the normal. You draw the normal. Now you have the light ray which is parallel to principal axis, and it is striking your convex surface. It is from a denser medium to a rarer medium. So now this is your convex surface, right? This is the ray which is traveling parallel to principal axis. Now it is going to bend away from the normal. If you see in this first one, you have rarer to denser medium, you have the normal ray traveling to parallel to principal axis. It bends towards the normal and it goes in a certain direction. Here the ray traveling to parallel to principal axis, it is from denser to rarer medium, it is bending away from the normal. So you have two cases. A ray traveling parallel to principal axis strikes a convex surface, passes from rarer to denser medium. Second, a ray traveling parallel to principal axis strikes a convex surface and passes from a denser medium to a rarer medium. Let's take the cases of concave mirrors now. These were the two cases where the ray was incident on a convex type surface. It was a outward curved surface where the two media were interacting with each other, rarer and denser mediums. Now ray is again traveling according to principal axis, but this time it's coming from the right hand side. So they are now incident on the inward curves, if you see. So if they are incident on the inward curves, this particular interaction is concave. So now ray is traveling parallel to principal axis. It is going to strike the concave surface. Now it is passing from a denser medium to a rarer medium. Draw the normal, and if you see, it's going to bend away from the normal. So you have a line which is a ray which is coming parallel to principal axis. This is your principal axis. Ray coming parallel to principal axis, and as soon as it strikes this surface, it is going to bend away from the normal, denser to rarer. Next, you have rarer to denser this time. So you again have this concave surface. You have a ray which is coming parallel to principal axis. You have the normal drawn. Since you have the normal drawn, you can easily draw the ray which will now bend towards the normal, since it is traveling from a rarer medium to a denser medium. So 4 cases, convex 2 cases, 1 denser to rarer, second rarer to denser, concave 2 cases, denser to rarer and rarer to denser. But the point here is that after refraction, the particular line or refracted ray is going to meet the principal axis at a point, or it is going to appear to meet at a point, because in case of some cases, it's the actual ray diverges from the point, so we have to extend it back, and since we extend it back, we will see that it will appear to be meeting at a point. I told you there are virtual images formed and there are real images formed also. So when here there are points where the refracted ray will actually meet, and there are points where it will appear to be coming from. So now let us focus on that. You have figure 4a, this is 4a, and you have figure 4c, which is this figure. In both cases, you have here a convex surface and here a concave surface. In both cases, you see that when light is traveling from a certain medium and light is parallel to your principal axis, after refraction, it goes and meets principal axis at a point. At 4C also, incident light ray is incident on the concave surface, and after refraction, it goes and it meets the principal axis at some point. In cases of 4B and 4D, here the light ray is incident parallel to principal axis, again incident on the convex surface, but it is bending away from the normal. So it is bending away from the normal, it's not really meeting the principal axis at some point. In 4D also, if you see this concave surface, now the principal axis is the line that is coming parallel to principal axis, it bends away from the normal. Both cases in 4B and 4D, the refracted ray is not meeting principal axis at any point. But if you extend this ray in this direction, see the direction of the laser point, if you extend this ray backward, then it will appear to meet the principal axis at a point. Let's say the point is here. Now, if you look at 4D, this is the ray. If you extend it backward, it will come and meet the principal axis at this point. So there are some point that it is appear to be coming from, or you can say if you extend this ray backwards, you will be able to assume, or you will be able to say that the refracted ray is coming from this point, right? Here also, if you extend this backwards, you will say that the ray of light is refracted rays appear to be coming from a certain point. So this points 4A and 4C, the point where the refracted ray is meeting the principal axis, or in these two cases where you are extending the ray backwards and it is appearing to meet the principal axis at a point. Parallel rays of light which are parallel to principal axis after refraction either meet at the point called focal point, or either they appear to be coming from this point. And this particular point where the refracted ray is appearing to either intersect the principal axis or actually intersecting the principal axis, this particular point is called focal point. It is represented by F. You have seen something similar even in our reflection of light chapters. So this point where rays parallel to principal axis after